So now we are moving forward with the our keynote 4. So keynote 4, unfortunately, that the Prof. Sabu Thomas is have some urgent issues, and that one. So we are going to play his recording. We request him to, because he is one of the another famous guy on the natural fiber and best composites, and well-known guy. So before going to his recording, I just want to give the brief introductions about the Sabu Thomas. Sabu Thomas is basically a founder, director, and professor in charge. And basically, presently, he is a vice chancellor of the Mahatma Gandhi University, Kottayam, India. And he is also the founding, what you call the director for Center for Nanoscience and Nanotechnology. And he's a full professor in the Mahatma Gandhi University. And his area of research is the nanomaterial, polymer nanocomposite, elastomers, polymer blends, and nanomedicines, a green nanotechnology. And he's also get a lot of awards from international. He's a fellow of the Royal Society of Chemistry and distinguished professorship from Joseph Stephen Institute, Slovenia, MRSI medal, Nanotech medal, CRSI medal, distinguished faculty award, and Sukumar Methi award for the best polymer researcher in the country. And he holds the positions of number 5 in the productive researcher in India, and very recently is out in standing contribution in the nanomaterial, polymer science and engineering. Prof. Thomas have confirmed honoris causa doctorate in science by the University of South Brittany, Lorraine, France. And he is co-author 43 books, and he is the inventor of 6 patents, and his H index is 77, and he have more than 26,000 citations. So we listen the Sabu Thomas keynote 4.
So can you see the screen now?
Yes, okay, we cleared the screen. You can just play the...
Very good morning to all of you. I'm extremely delighted to be with you. I am Sabu Thomas, Vice Chancellor of Mahatma Gandhi University, Kottayam, Kerala, India. I'm giving a lecture on circular economy, new opportunities in sustainable green nanomaterials. In this conference, in this meeting, I'm going to talk about the green chemistry approaches by which we can develop new bio-nanomaterials, bio-nanocomposites for preserving our ecosystem. According to American Chemical Society, we produce 1.6 million tons of agro waste every year. These agro waste are being wasted, not really used for meaningful applications. Quite a lot of waste. And let me show you the next slide. If you look at the agro waste being produced worldwide, quite a lot of sugarcane bagasse after producing sugar. Wheat bran and rice bran, corn cob, wood flour, wheat and rice straw. For a lot of other fibers like jute, coir, pineapple, hemp. Fish industry, we produce a lot of waste, crab shells, prawn shells. And if you look at the starch, we have a lot of waste starch from agricultural feeds, potato, cassava. If you look at the commercial production of this material, you will see wood flour is number 1, followed by bamboo, cotton, jute, henna, quite a lot of fibers. Plant fibers have a lot of potentialities. They are environmentally benign materials, cost effective, abundant, non-abrasive to machineries. They have fantastic acoustic and thermal insulation properties. They are underutilized, they're renewable, there are lots of positive attributes. We can classify these fibers based on their origin. We can extract them from the stem. We call them as bast fibers, from the leaf, Leaf fibers, the seed or food, called seed fibers. Grass, good example is bamboo fiber, elephant grass. Let me show you some of the nice photographs. You can see a banana plantation, banana fiber extract from the stem of banana, oil palm, pineapple leaf fiber extracted from the leaf of the pineapple. Look at the choir. Kerala has lots of choir. Kerala is a place of open trees, so we have lots of enterprises based on choir fiber. Let us look at the relative price of these natural fibers. If you look at cotton, take it as an index of 100, you will find that once the fibers like jute, sisal, coir, straw, they are all quite cheap. They're quite cheap. Let's now look at the physical-mechanical properties of these fibers. They're pretty strong. I've mentioned the tensile strength, Young's modulus, elongation rate, density. But if you take the specific properties, property divided by density, you will find that they can beat glass fibers because they are much denser than glass fibers. Let's now look at the chemistry of this material. Essentially, they are cellulose. Look at the chemistry of cellulose. They're beautiful hydroxide. A chemist can do wonders. And this is lignin, a composite hydrocarbon. Then you have wax, pectin, 8 to 10% of moisture in actual fiber. Let me now show you the hierarchical structure of plant fiber. You can work in macro length scale, macro fiber. You can work in micro length scale. I remember when I started my career in the university in Mahatma Gandhi, Kottayam, we have been quite active for natural fibers on micro length scale. We drop microfibers and plastics. But now our focus is more on nano length scale. We do a lot of work on nano length scale. Why nano length scale is so important? Why nanocellulose is so important? High water holding capacity, highly crystalline, low density, high strength, high specific properties. So there are 18 reasons for fantastic, sustainable materials for development. If you examine this nanomaterial under electron microscope, you see a web of network-like structure. This is nanocellulose. It's pretty long. You cannot measure the length of this fiber. But the diameter is in range of 10 to 30 nanometer. And if you take this gel in a transparent glass, it looks like this. And you can produce by a variety of techniques, as hydrolysis, steam explosion, high-density ultrasonication process, crushing, grinding, high-pressure homogenization process. High-pressure homogenization is nothing but you apply high pressure. Then you separate these fibers into nanoscale. Essentially, you apply high shear. If you look at super grinding, adopted by the Japanese group, here also you apply high shear force. You have a static stone and a rotating stone, and you pass a slurry between these two stones and you separate the fibers in the nanoscale. While crushing, you cool down to sub-zero temperature. When you crush it, you get nano fibers. High-density ultrasonication process, where you apply high mechanical force, which oscillating power is used to isolate cellulose fibers by hydrodynamic forces of ultrasound. Steam explosion process, you can see this is natural fiber subjected to high temperature and pressure. And then in a jacketed system. We call it a steam explosion chamber. And then you suddenly release the pressure, then you have an explosion. The system is opened up, the cellulose structure is opened up, and you have chemical hydrolysis of hemicellulose, and you get. Look at what we do in our laboratory. My PhD students collect agricultural waste from plantations, clean them, chop them into smaller lengths. We treat with the alkali, remove lignin hemicellulose, you get a slurry, and then we go for acid hydrolysis, either a strong acid or a weak acid. If you use strong acid, you get nanocrystals. If you use weak acid, you get nanocellulose. Look at the milky liquid. This is nothing but the dispersion of nanocellulose in water. And if you examine under high resolution electron microscope, you see beautiful structure of nanofibers. Look at the structure of nanocellulose. You have crystalline and amorphous segments coexist. This is a case of nanocellulose. Use a light acid. Use a strong acid, you get short nanocrystals where you kill all the amorphous phase. Dear friends, nanocellulose is very high modulus, close to 130 gigapascals, and very high strength. Typical polymer modulus is maybe 2 or 3 gigapascals. So nanocellulose offers high modulus, high strength. Look at nanocrystals made by Mahatma and group from wood flour. Mahatma used strong sulfuric acid, 65% sulfuric acid, starting to make this wood flour. Let me show you our manufacturing setup in the university. We collect the raw fiber from the plantation, put into small pieces, put into the steam explosion chamber. Then we do a bleaching process, acid hydrolysis. Sometimes we repeat the process till you get nano. Then you get a centrifugation process. And finally, we get beautiful nanomaterials. Let me show you some of the structures we have developed. This is nanocellulose developed by my former co-worker, Vipin, and India Brazil Corporation from Nanoscale. Nanocellulose derived from wood flour. Thanks to Vaishak, we made beautiful nanocellulose from wood flour. Nanocellulose from pineapple leaf fiber. This is an FESCM picture by steam explosion process. Dear friends, we can also make quite a lot of chemistry on the surface of nanocellulose. Look at this. This is nanocellulose structure. We can do a lot of chemistry, esterification reaction, chemo-mediated oxidation process. We can do fluorescent labeling. We can do catalyzation reaction. We can do cellulation reaction. We can do polymer grafting. So a variety of reactions could be performed on the surface of cellulose. Recently, we have signed an MOU with a car company in India. We are going to do cellulation reaction so that we can make the surface. So dear friends, we can play with the chemistry of the surface of these nanomaterials by doing very simple chemical reactions. So let me now come to the utility of this material. We can use them for water purification. We can use them for EMI shielding, wound healing, conductive applications, sensors. Let me now talk about water purification. For water purification purpose, my former coworker made use of a bilayer configuration. Look at this is the commercial filter you get. Commercial filters have a non-woven microfiber support. At the top of that, you have electrospun nanofibrous substrate. This is PVDF, the top one. You know what we have done? We have done a coating of nanocellulose on the surface. Okay? Spray coating. And what we try to do is we try to remove crystal violet dye. There are a lot of textile industry in India, they pump out these waste into river water. You can see the violet color of the water because the crystal violet. We want to remove this very efficiently, and my PhD student did a small chemistry. This is nanocellulose. We reacted with the meltrum acids, the green chemistry, and you can see negative group on the surface, CO minus group on the surface of nanocellulose. Very interesting green chemistry. And if you do that, look at the efficiency of separation process. This is a commercial filter you get in the market. Removal of crystal violet dye, you can see absorption capacity as a function of time. This is after coating with nanocellulose on the surface of the commercial filter. The top one is chemically modified nanocellulose. You see the separation efficiency is quite good. But dear friends, we can make fantastic filters by using nanocellulose. And if you look at the chemistry, this is the chemically modified nanocellulose. This is a crystal violet dye. It can form electrostatic interaction. The dye and the nanocellulose. You can see all these crystal violet molecules have been retained at the top of the filter surface. Dear friends, we can remove suspended particles from water. You know, water is increasingly contaminated with a lot of suspended particles. What we have done is we bought the commercial filter and gave a coating of nanocellulose dispersion. Once you give a coating, the whole size becomes something like 8 nanometer. Therefore, most of the suspended particle in water will be removed. You can see a beautiful picture. We try to remove iron oxide particle. This is after filtration process. You can see all the iron oxide particles have been retained the top surface of the membrane. This is the bottom part of the membrane. You can see the impure water, and this is the pure water. You can see the transmittance. Impure water, you see zero transmittance. Pure water is almost 100% transmittance. Now let me show you some of the work did by the Finnish group. Finnish group wanted to purify water in the sea. You all know that water in sea is increasingly contaminated. Particularly from ship, we have lots of incidents where water is leaked from the ship, or there will be several cases where ships sink in sea. Therefore, we need to have methodologies to purify seawater. So what the Finnish group did is they made aerogel of nanocellulose. And then what they did is they made the aerogel surface hydrophobic by a titanium dioxide coating. Once you do that, the oil could be absorbed by the aerogel. You can see this red is the oil. You sprinkle in seawater, the oil in seawater could be absorbed by this nanocellulose. But water cannot get in because you made the surface hydrophobic. And once oil is absorbed, you can recycle the oil or you can burn. This is a very good technology by which seawater could be purified. Dear friends, we can remove nickel, we can remove chromium, we can remove lead. We want to remove chromium 6, which is negatively charged. What you do is you do a small chemistry. You react nanocellulose surface with polyvinylamine. Once you react with the polyvinylamine, you introduce positive charge on the surface of nanocellulose, and you can see the removal of chromium 6. You can remove nickel, cadmium, lead. So dear friends, we can remove different types of metallic impurities from water. Similarly, we can also remove bacteria and viruses. Water is contaminated with the bacteria and viruses. Now we are all facing the corona pandemic. So we have solution using nanocellulose to remove bacteria and virus. I can show you a couple of examples. We want to remove bacteria. Bacteria are bigger in size, so you can remove by size exclusion principle. You give a coating of nanocellulose on the surface, bacteria could be removed by size exclusion. Extremely conductive. Look at this. Very lightweight material and conductive. Let me now show you some of the work we are also doing in with respect to chitin from seafood waste. We are particularly focusing on the crab shell and prawn shell. If you look at chitin, the structure is very similar to cellulose, but we have a beautiful NH3O CH3 that makes a big difference. This is a fantastic material, the second most abundant material in the crust of the earth after cellulose. Dear friends, one can make nano crystals of chitin or nanofibers of chitin. If you use a strong acid, you get nanocrystals. If you use a weak acid, we get nanocellulose. So it's a simple acid washing. You remove all the protein by washing. Let me show you one slide. A very interesting work. This is a structure of nanochitin. This is hydrophilic. You can introduce alkyl chain on the surface. You react to the bromohexadecane. Alkyl. Let me now show the next slide. Look at this slide. This is neat nanochitin, hydrophilic, contact angle 86.5. If you increase the number of hydrophobic group, you see, dear friends, look at sample H. You can make super hydrophobic surfaces. The contact angle of 158.2. And dear friends, this is an excellent additive for oil. It's positive modifier for oil or hydrophobic oil, and you can make excellent. This is a neat chitin nanoviscose, and this is increasing number of hydrophobic groups. Once you put a lot of hydrophobic groups, you have population forces and they agglomerate. Fellowship. Siraj Gobi, the combined PVDF and nanochitin. Hybrid structure even for a electrospinning process. For the removal of indigo carmine dye. Dear friends, if you use only PVDF, the separation efficiency is 23%. But when you combine PVDF and nanochitin together, look at this separation efficiency, 89.9. You can get a very high separation efficiency. Removal of dye. When you combine PVDF and nanochitin. Dear friends, I'm going to show you the last phase of my talk. Starch, nanostarch. If you see the plantation, agricultural plantation, you see a lot of waste potato, waste tapioca, waste rice, waste wheat. This is cassava, tapioca. We have plenty of tapioca in Kerala. Here also you can use an acid washing. You wash the tapioca, the starch with acid. You remove all the unwanted material and you get nano crystals of starch powder. If you examine under electron microscope, you see the nanoparticles of starch. This is from waxy maize. And dear friends, I'll show you one slide what we have done. A PhD student of mine, she worked with natural rubber latex and nano starch. This is a neat natural rubber. And if you put increasing content of nano crystals of starch, you see the modulus goes up. Rubber is transformed into a high modulus material. You can see a beautiful cartoon made by PhD student. You can see the macromolecular chains and network of nanocrystals of starch, which actually immobilize the macromolecular chain. You get a very high modulus and strong. Dear friends, I'm going to conclude my lecture. Agro waste could be transformed into advanced functional green nanomaterials. From cellulose, we can make nanocellulose and nanoviscose, and you can use it for an enormous number of applications. Reinforcing pillar in polymers, water purification, wound healing, energy storage, my shielding, so many applications. Similarly, look at the nanochitin. From fish industry waste, we can make nanofibers or nanochitin biscuits used for water purification, soil purification, structuring of oil, this additive for oil. Similarly, look at starch. We don't touch the the food sector, where we collect the waste, good material for reinforcing polymers. Dear friends, I'm posing a question to all of you. Can we become a zero-waste planet? My answer is yes.
Okay, thank you, Dr. Midani, for sharing the video recording of Prof. Sabu Thomas, and we are thankful to Prof. Sabu Thomas on behalf of BIPALMA 2021 for giving. We will look forward to get him live or through the physical conference in the future. He's agreed to us that in the coming time. So from there, we are going to end the keynote session. But